Okay, so we're talking about if you go into the extrema.pdf, um, extrema.pdf, we have the operator, the upside down triangle. So upside down triangle, I think the word for it in LaTeX at least, that's the terrible triangle. Boom. We call this nabla. I don't know why we call it nabla. Um, I really, I really don't. But um, what are the parts? What are the parts? The parts are E sub k's and delta k's. Um, so nabla is defined as it's not. We're not going to do a very good definition. But it's literally just k equals 1 to n of ek and essentially del xk. So what does that mean? So ek is the standard basis, and I hope you remember what standard basis is from linear algebra. But essentially, in R3, E1 is defined as 100, E2 is defined as 010, E3 is defined as 001. It means standard basis, which is essentially the column space of the identity matrix. The column space of the identity matrix is sort of, well, I wouldn't say column space, but I would say the columns of the identity matrix. The column space is the span of those columns. So I know, like in R7, E4 is defined as 1, 2, 3, 4. The fourth component is a 1. 1, 2, 3. That's E4 in R7, right? So you need an ambient space and you need a number. So I'm going to leave that up here because I don't want to erase it too quickly. I mean, it's a YouTube video. You can pause it if you don't want me to erase it too quickly. And essentially, the del xk's are higher order functions, meaning that they're functions that take functions as input and return functions as output. I mean, nabla is a higher order function. Higher order function is just a programming word for a function that takes a function as input and returns a function as output. So what's the simple case? The simple case is for scalar field is just Rn into R. For scalar field, gradient of alpha, we call it the gradient of alpha, which is nabla, and then just alpha. So what would that be? That would be sigma of ek del k of each alpha k. And I forgot the k here. Because we remember that alpha is defined as the function taking x into alpha 1x, alpha 2x, dot, 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 alpha nx. No, wait, I'm totally screwing this up. Excuse me. Excuse me. It's just this. This is the gradient of alpha. So you probably want to see an example. I mean, there aren't there examples in the notes. Well, the exam is examples, but I mean this is pretty straightforward. So what this means is that gradient is now crucially gradient is actually a row vector, but we're going to call it a column vector for now, because the syntax gets too complicated if you don't do that. This is del alpha del x1 dot 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 del alpha del xn. Terrible bracket. Also a terrible bracket. That's a slightly better bracket. Right? So that's basically the money. Alpha del xn. Del alpha del x1 through del alpha del xn. All right? That's all you got to do for gradient. If you know how to take partial derivatives, you know how to do gradient. So what the heck is divergence? What the heck is, for vector field, and I'm going to do something that Bocce does, and it's not going to make sense. How do I want to explain this? For vector field beta, I'm just going to recycle alpha. For vector field, alpha is defined as Rn into Rn. Okay, so I have to explain something about vector fields. Bocce is asking you to write the signature of a vector field as this. Rn cross Rn. And the reason for that is a geometrical phenomenon that I could not dissuade him from filling your head with. So on Wikipedia and in the Deneen book, vector fields are Rn into Rn. But Bocce wants you to think of them as Rn cross Rn as the codomain, which is pretty annoying. But let's think about what would nabla dot alpha be when alpha is a vector field. So this is what the divergence would be. Well, we know that nabla, so this is really going to be a function, right? It's going to be a function that takes some x in Rn and lands it here. From, I believe it's Rn, we'll just say into Rn. But it's a dot product. So what does that mean? Now the sigma, the sum of standard basis vectors times partial derivatives is a vector. This is going to be del x1 dot 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 del xn. Because if we have let n equal 3, sigma of ek del xk equals 101 del x1 plus 010 del x2 plus 001 del x3. x3. I should maybe write a little bit slower because you can watch this on 2x speed, and if I write slower, it'll be clearer. So, that's a 0. That's a terrible 0. And that's a 1. So this is none other than del x1 del x2 del x3. So what's the difference between this and the gradient of the scalar field? Well, we plug in alpha, right? So if we apply alpha to this vector, or apply this vector to alpha, I always get those screwed up. If we apply this vector to alpha, we get a vector of functions. However, what we're doing now is we're taking the dot product with alpha. Alpha 1 dot 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 alpha n. So what's an example alpha? So an example alpha is a function taking xy into, let me go green here. And let me erase this let n equals 3 business. Because I just wanted to be exceedingly clear what's going on with the sigma of EKs times delta of x's. Delta del x1. Let alpha equal xy into xy x plus y. This is a vector field. This is a perfectly nice vector field. Okay? Then alpha 1 would equal the function taking xy and mapping it to xy from R2 into R. And alpha 2 would equal the function taking xy and mapping it to x plus y. From R2 into R. Okay? So the dot product here is just going to equal del of alpha 1 del x1 plus dot 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 plus del of alpha n del xn. Which is none other than the sum of alpha k del alpha k del xk for k equals 1 to n. And maybe I'll pull out LaTeX and I'll write this up. Because his notes could be a little better. Honestly, this is sort of what he gave us in lecture when we took the course. But yeah, these notes could be a little better. And we're not going to talk about this operator because I don't think you need it for this exam. But we have to talk about gradient, divergence, and curl. So what is curl? Curl is just the cross product. So that's divergence, okay? Gradient's easy because gradient is a vector where all of the alphas are all the components of the vector are partial derivatives of alpha. The gradient is the vector of partials, and vector of partials can mean only one thing. It can only mean the vector where each component is a partial for that component. Now, what do we think what do we think curl is going to be? So I caution you, curl. I'm going to make a new page for curl. I caution you that curl nice sandy color. It always looks nice on the black background. Nabla cross product with some function is defined as a function taking alpha into nabla cross alpha, where cross is the cross product from R3 to R3 into, I believe, R3 into R3. So this gets a little nuts. Whereas before, so here's the thing about divergence and gradient. Divergence and gradient are defined for any n. Okay? Curl is well understood in R3. And if you take a differential geometry class, you can talk about higher dimensional curls. Okay? But in your undergrad physics courses, you need curl in R3. So let me just write that down. Gradients and divergence are defined for all n, i.e. gradient is defined for Rn into R, and divergence is defined from Rn into Rn. For functions. Curl is only defined for vector fields in R3. Alpha R3 into R3. I think this is the right signature. So let me go back to the sandy color, which I like. I like the sandy color a lot. We have, imagine what Nabla cross product would look like. So if we remember what a cross product is a cross product is an n-1 operator. Meaning, the number of arguments it has is one less than the number of dimensions you're in. The number of arguments it has is one less than the number of dimensions you're in. So in R3, that's really simple. It's a binary operator. So if I have U1, U2, U3 cross V1, V2, V3, this equals the determinant, the symbolic determinant of E1, E2, E3, U1, U2, U3, V1, V2, V3, where E1 through E3 are the standard basis vectors. The standard basis vectors. So what that means is we have 1, 0, 0 times the determinant of U2 here. And you might need to review determinants. U2, U3, V2, V3 minus 0, 1, 0 times the determinant of U1, U3, V1, V3. I'm not reviewing determinants in this video. This video is not reviewing determinants. plus 001 det U1, U2, V1, V2. Okay? So I did just review determinants. I effectively just reviewed determinants because I reviewed the cross product. The cross product is just a 3x3 determinant where the top row is standard basis vectors. So what do we think? Nabla cross product with alpha for alpha is an R3 into R3. This can be none other. So what that means is alpha equals alpha 1, alpha 2, alpha 3. Okay? Alpha is a vector of scalar fields. In other words, it's a vector field. So this is going to be del x1, del x2, del x3. Cross alpha 1, alpha 2, alpha 3. So this is none other than the symbolic determinant of E1, E2, E3, del x1, del x2, del x3, alpha 1, alpha 2, alpha 3. All right? And so we're playing fast and loose with notation. We are playing fast and loose with notation. Because we're talking about multiplication and function application in a very fast and loose way. So this formula is going to be, and the E1 is going to be del x2, del alpha 3 of del x2 minus del alpha 2 del x3 minus del x1 of alpha 3 minus del alpha 1 of del x3. And it's really the function, okay? It is really the function. Watch this. It's really taking it's so hard to go back into pen mode. There you go. X1, X2, X3. The result of curl is a function, right? And last but not least, I have E3, which is this component, times this determinant. So that's del alpha 2 del x1 minus del alpha 1 del x2. Am I right? I'm right. So this is the curl. Okay? So I've done gradient, divergence, and curl. And if I find time, I might write up some notes in LaTeX because his notes leave a lot to be desired. This is all he gives you. this is all he gives you, and I just unpacked it for you, okay? That should be all the unpacking you need, and then you'll be able to do the exam.